Hi all, welcome to myclass.com. Quicksort. In this lesson, we are discussing about quicksort, its algorithm and its analysis. Let's start. Like merge sort, quicksort also uses a divided and conquer approach. We are dividing the problem into subproblems. Like that, we are doing the sorting technique. And also a stable algorithm and a not in place algorithm also, because quicksort also uses more varying memory according to the number of inputs. Next point is the best and average time complexity is order of n log n. Like merge sort, in merge sort also best, worst and average all are order of n log n, but in quicksort, best and average are order of n log n, but the worst time complexity is order of n square. Remember, best case is order of n log n, worst is order of n square. Quicksort is a not in place algorithm. Because of that, the space complexity is related to number of inputs in the unsorted list. So we can say that the space complexity of quicksort is order of n. Unlike another algorithms, this algorithm is quite efficient for large-sized data set. Our bubble sort, insertion sort and selection sort all are not suitable for sorting a large-sized data set, but quicksort is very efficient for large-sized data set. As the name mentioned, it is a quicksort. Quicksort doing the sorting techniques very quickly, but although the name is quicksort, but it is not the very quickest sorting algorithm, even though the name is quicksort. Understood? First of all, we are just going through the quicksort algorithm. The quicksort algorithm mainly related to there is a pivot variable, pivot. Pivot means there is a pivot point or pivot element. We are selecting one of our element as a pivot, and then our aim is to find the proper index for our pivot element. That is the concept of quicksort. Okay. So for that, our algorithm looks like quicksort A start and end. We are passing the whole array and start and end index. Then begin if start is less than n. That is the base condition, and we are beginning. We are doing 3 steps inside this. What are they? This is partition A start and end. This is the main process of quicksort. This procedure is to find the correct index for the pivot value. So this is the works done in the partition A start and this all we are explaining with the help of an example next. Okay. Now just look at the whole algorithm steps. After that, after finding the pivot index, we are dividing the problem into 2. That's why we are saying that quicksort also uses divided and conquer approach. So let's assume that this is our pivot variable or pivot element. You can select the pivot according to your criteria. That is, we can select as a first element as our pivot, and also we can select our last elements also our pivot element. Also, you can randomly select our pivot. Let's assume that 65 is our pivot in this particular example. So our aim is to find the particular index for the 65. That means that place is the correct place for 65. So like that it is doing. When calling partition A start and we can find our index for our selected pivot point, pivot element. So after finding, we are partitioning quicksort A start pi pivot index minus 1. So we are partitioning this problem into 2. Quicksort start pi minus 1 and also quicksort A pi plus 1 up to end. So we are partitioning this problem into 2. And one point also that after finding the correct index for our pivot element, we can easily set that the left side of our pivot all are lesser than our pivot variable, but it is not in a sorted order, but it is lesser. In the right side, all elements are greater than our pivot. So that is the quicksort concept. So how we can find the correct index for our pivot. That is done in partition A start and procedure. So now explaining how can we find correct index for our 65. So let's do. So in the partition A start N, we are passing whole array and the starting index 0 and end as 8. Okay. After passing like that, we are setting a pivot index, pivot value, that is start. The starting element is our pivot value. So pivot is start, and also we are starting from I equal to start. So I equal to 0 in this point, and j equal to n plus 1, that is 9. So we want to start from here. So we are setting j equal to 9 because we are doing here do while. So we want to decrement, and after decrementing we are starting from the last element. Because of that we are setting j equal to n plus 1 by the assumption that there is a very bigger value infinity as a last element. So that is the concept. After that, this is while I less than j. This while loop is working up to I became more than j. I became equal to j or more than j. Then what is we are doing? Do I plus plus while. So this is the one do while statement, and the another is the another do while loop. Two do while loops are there. So for that our aim is to interchange. Our aim is to for I. This I pointers we are using to find the value that is bigger than our pivot value. Okay. So it is incrementing up to we are reaching a biggest value when compared to pivot. So our do I plus plus while a of I less than or equal to a of pivot. If a of I is less than or equal to a of pivot, we are incrementing. Again this condition is true, then we are incrementing. When we have reached an element that is greater than 65, then we are stopping the incrementing of I value. Okay. Here also we are decrementing j value while a of j greater than a of pivot. If we are getting a number that is greater than, then we are decrementing. Again we have found a greater value than the pivot value, then we are decrementing. When we are reaching a value that is less than 65, then we have stopped the decrementing of j. We are stopping the. With the help of this do while, first do while loop, we are finding a value bigger than the 65, and the second do while is for finding a value lesser than the 65. Okay, so let's start with I equal to 0 and j equal to 9. Our pivot value is 65. So I is less than I. 0 is less than 9. It is true. Then do I plus plus. Now I is pointing into 1. Then while a of I, then we are checking the while loop. Isn't do while is like that. So a of I less than. Is a of I is less than or equal to a of pivot? No, it is greater than. So it will stop the. Now found a correct I value that holds a greater value than 65. Now we are going to the another do while loop. So first we are decrementing j. Now j equal to 8. After that we are checking while a of j is greater than a of pivot. No. If it is true, we are decrementing again our j, but it is false. We have stopped here. So we have got 1, I equal to 1 and j equal to 8. So after this to do while, we are checking another condition. If I less than j, here we have I equal to 1 and j equal to I. So I less than j is true. Then we are swapping a of I and a of j. Our aim is to change the lesser value to left side and greater value to right side. Okay, that is our aim. So after that we have got like this. So our I equal to 1 and j equal to 8. Now we are swapping this because I less than j, we are swapping a of I and a of j. So now 45 is here and 70 is here. Now also our I equal to 1 and j equal to 8. Okay. Again we are inside this while loop itself now. Again we are checking I less than j. Yes, it is I less than j. Now again we are incrementing I value I equal to 2. Then checking a of I is less than, not less than. So we have stopped here. Again this do loop also. This do while loop also we are decrementing. So now j equal to 7. Then A of j greater than A of pivot? No. So we are stopping here also. Now we have got another two value for exchange. So swapping 75 and 50. If I less than, here I equal to 2 and j equal to 7, it is also I is less than j, so we are swapping. Okay, so after swapping, we have reached this state. Okay. Now again we are checking our I equal to 2 and j equal to 7. I is less than j, true. Then we are again incrementing I value. Okay, again incrementing I value and again decrementing j value when we are executing this do while loop. After that we are again checking if I less than j. Yes, I less than j. Then we are swapping again. This process is repeating. Okay. So 55 is here now and 80 is here now. Okay, so at that moment I is 3 and j is 6. Again 3 is less than 6. Again this while loop is working. So do I, incrementing I. Incrementing I means I equal to 4 now. Then checking while A of I less than or equal to A of pivot. No, more incrementing is not possible. Now again another do while loop, we are decrementing j value, j equal to 5, A of j greater than A of pivot. No, it is lesser. So we have stopped here and now we have got another I and j value. I equal to 4 and j equal to 5. Again I is less than j, so we are swapping this value also. After swapping, we have got 60 here and 85 here. Now the I value, this is our I value, I equal to 4 and j equal to 5. Okay. Now we are going to this while loop. Yes, is it? So I less than j, now also I less than j. Now we are incrementing I value. Our new I value is 5 and new j value is, I value is 5. So 85 is not greater than. So we are stopping here and here we are decrementing j equal to 4. 60 also lesser than 65, but we are not, so we are stopping here. Now we have got new I and j value, but actually we have already done all the exchanges, but we want to stop this while loop. So that's why we are checking a if I equal to I less than j here. So after the new value of I equal to, after the new value of I equal to 5 and j equal to 4, this condition should be false, I less than j. So no swapping will occur here. No swapping will occur here. Now we are checking I less than j. We didn't come out from this while loop. So we are checking I 5 is less than 4. No, it is false now. So we are coming out of this while loop. After this coming out of the while loop, our main aim is to track our j value. J is equal to 4 and I equal to 5. It does not matter what's the value of 5. We are concentrating on the value of j. Now we are swapping a, that is the actual place for our 65. So we are swapping A of pivot and A of 60. Okay, now we are swapping. So this is the actual place for our 65. Now we are swapping A of pivot and A of j. So after swapping, our list should be like this. See, so 65 is the correct place for, so 65, the index 4 is the correct place for our 65 pivot value. Then we are returning that j value. So when we are calling this partition A start, and we will get the correct index for our pivot value. Understood? That is, so after that our quicksort is calling this portion and this portion again. It's a recursive call. Okay. So let's discuss that now. So now we have reached here, 65 is in the correct place and we want to call quicksort A start pi minus 1, pi minus 1. So we are starting from here and also we are quicksort A pi plus 1 to end. See, now we are calling this quicksort to this portion first. So this is executing, this is pending here. Okay, let's remember that. Now 60 is our pivot value. After calling this partition, we will get the correct index 60. So that is 3. Now there is no right partition, only left partition is there. So we are doing that left. So 55 is the pivot. We are finding the index value for 55 by calling partition A start and end. Now here also we have only left side too. So left side is here. So 50 is now the pivot value. We are getting the correct index for 50. Now we are calling 45, but only one element is there. So if start less than, and here is start is also 0 and end is also 0. So it will be false. Okay, so let's stop here, and 45 will be in the correct place. Our control is go to the pending quicksort right part. Okay, in this part also we are doing the same thing. We are finding 85, correct place for 85, then correct place for 70, correct place for 70, then correct place for 80, and correct place for 75. So after that, all green colored value is in the correct index. We will get the sorted list of the left parts and so sorted list of the right part of 65. So after that we will get the sorted list. That is the concept of quicksort. Hope it is clear. We want to analyze quicksort analysis. At introduction part, I told that our worst case time complexity is order of n square, but best and average case complexity is order of n log n. Now let's analyze that thing first. Okay. Actually, there is a very difficult to find a best case for quicksort, but when it happened, what is the best case for quicksort? Actually, if 9 elements is there, so we will find pivot correct index value for our pivot variable. If it is in the correct middle part, then we can divide this portion into correct division. See, when we have found the correct place for our pivot value, that is the 4, we can divide this portion into correct division. We can divide this problem into same subproblem, same length subproblem. That is the best case for quicksort. Actually, it happens when we are selecting pivot value, our middle value. Pivot value is median. When we are always selecting median as our pivot value, then it is equally placed at the very center. Then we can divide this problem into correct division. We can divide this problem with correct division. So that is the best case. So when a best case happen, if n is the total number of elements, we can divide this portion into like this, n by 2, n by 2. Then we can do like n by 2 by 2, n by 4, n by 4, n by 4, n by 4. Okay, so our problem is, this is like n by 8, n by 8. N by 8, like that is going on. This will end up to this partition. The elements in this sublist contains only one element. See, this division we can write like this. See, n by 2 raised to 0. Here n by 2 raised to 1. Here n by 2 raised to 2. Here n by 2 raised to 3. So like that we can generalize after the kth level. We can say that n by 2 raised to k. It will end at last when the sublist containing only one element. See, so we can write n by 2 raised to k equal to 1. So we can easily write n equal to 2 raised to k. So that is the logarithmic connection. So we can write log n equal to log 2 base to k. So we can easily set that k equal to log n. So number of levels in the subdivision in the best case. When we are dividing in the problem into correct half part, we can say that this problem will occurs in the log n level. Each level we are handling n elements. See, in this level also n elements we are handling. In this level also n by 2 plus n by 2 n level. Here also 4n by 4, that is n levels, n elements we are handling. So it is related to n times we are doing work. So we can easily set that each level n time working is the total how many levels are the log n. So n log n. So that is the best case and also average case for quicksort, or n log n. Okay. Best case, best and average case for quicksort is n log n. Now we want to analyze the worst case scenario of quicksort. So what should be the worst case? Actually, our input elements is in the sorted order already. That is the very worst case, because when we are selecting a pivot value at the end or at the first, after the finding the index value for our pivot value, it is the same index itself. Okay, see, 1 is in the correct place, so it is the correct place for our value 1. Then, so here the working is on n elements. Now this is in the correct place, so the division is in the second layer we are doing with n minus 1 elements. In the third layer we are doing this partition with n minus 2. Now this is n minus 3. This is going on up to one element is remaining to be sorted. See, so our levels are going like this. Our working is doing like this. N plus n minus 1 plus n minus 2 plus up to 2 plus 1. So this is the natural number summation series. So there is up to n. 1 plus 2 plus 3 to up to n. Okay. Not n minus 1 in bubble sort, selection sort and insertion sort. It is up to n minus 1, but it is up to n. So our result, we can generalize it as n into n plus. So the result of this is n into n plus 1 by 2. See? So n square plus n by 2. So that is n square by 2 plus n by 2. We are selecting only the biggest exponential term. So the worst case of quick sort is big of n square. Okay? And we have already said that the space complexity is in terms of n. Sometimes it is also said that the space complexity is based on n log n. In the best case and average case, we can say that the space complexity is based on n log n, because the division is in the correct partition, so we are handling with such memory location. But in this case, we can say that it is in terms of n, so we can easily say that the space complexity is order of n. But generally we are saying that the space complexity of quicksort is order of n. So that is all about our quicksort. We have analyzed the algorithm and we have got the best and average time complexity is order of n log n. The worst case is order of n square. And the space complexity is order of n. We can also set in the terms of n log n also. Hope it is clear now. Any doubt you can ask through comments, and thank you.